Okay, welcome back. My name is Jesse. I am a tutor in Melbourne and I also make GAMSAT videos as well. And today what we're going to do is go through the fourth installment of the Chemistry Crash Course for GAMSAT Section 3. We're going to be looking more at organic chemistry. We did the first one last week that went through just the kind of principles of IUPAC naming and some of the nomenclature and structures around organic chemistry and what it all is. What we're going to do now is dive into the organic reaction pathways, and because it's a relatively small topic, we're also going to put in acid and base chemistry and equilibria. People have asked for that, so they've found that a little bit tricky. There's a little bit more on kind of logs and stuff. If you look at the logs and exponentials video that I did for maths, I do a little bit more calculation in relation to pH and pOH and pKa values and stuff. But it was very much maths based. So if you're looking for that, check that out. Otherwise, we're going to look more at the chemistry side of things today to kind of hopefully clear that stuff up as well at the end. Okay, so first of all, organic chemistry it's a big topic, and it's the bulk of the chemistry that you'll see in Section 3, right? Again, as I always say at the start of all these videos, this is content based, but the test is reasoning based. I'm still trying to make these as much about the reasoning than the content itself, but it's somewhat unavoidable, and these are obviously for people with either no background in chemistry or science, or people who have not done it in a while need to refresh their skills. And so, disclaimer as always, yes, it is a reasoning test. No, they're not going to assess direct content, but familiarity with content and these kind of principles is really important. A lot of people don't really maybe appreciate exactly how far a science degree gets you in terms of being familiar with a lot of the jargon and the applications of it. So for people that are watching right now that don't have a science background, it can be a bit of a nightmare, and it can be quite confusing because there's a lot of kind of jargon that goes along in there. So that's what we're going to clear up as well. All right, so first of all, we want to think of organic pathways as being like rearranging Lego bricks, right? So yes, there's some chemistry in it, but a lot of the time they're going to give you a pathway that you're completely unfamiliar with. So even if you'd done a science degree, you would have no idea what you're looking at. And I can say that because like I look at the questions and half the time I go, I've never seen this before. I've never seen that word before. I have no idea what's going on. And I just have to go, okay, it's a pattern that I'm just looking at relating the structures to each other and working out what changed if they didn't already describe it for me. So if we think of it as Lego bricks and you're just thinking, okay, I'm just shuffling the Lego bricks around, right? So we can see here, I've just done like literally a little picture of Lego bricks. And so you can see that all I've done here is moved the pink brick, right? I'll just get this. So the pink brick here has just moved over to this position in the final product. So we've got reactant, product, cool. And then from there I go, all right, so that's the pattern. Pink brick, whatever that is, whether it's an OH or a methyl group or this or that, I go, all right, that thing that looks like that, even if I don't know the name of it, move that to the other spot, right? And then I should be able to extrapolate that and use that in other compounds. So I go, okay, look for the pink thing, move it to the kind of top left corner, right? So you're relating things more visually overall. And this helps remove the need to kind of rely on too much kind of rote learning or memorization of things. I've also put like just a quick list of do's and don'ts. So do's are going to be things like rearrange position of atoms. That can happen in an organic pathway. We've seen that here. You can also break and form bonds, and that also includes the formation and the breaking of what we see as double bonds and triple bonds as well. These are actually going to be preferentially broken in a reaction pathway, so look out for those. That's the whole point of an organic pathway. It's just another reaction. Reactions are the breaking and reforming of bonds in different configurations. The don'ts, though, are going to be do not substitute a hydrogen that is attached to a carbon. So if it's directly attached to a carbon, it will not substitute. It will stay there. You need it to be attached to like an oxygen or a nitrogen in order to even attack it or remove it or replace it in some way. Carbons with more than 4 bonds is also a big no-no. So you could go right into the electron configuration of carbon and see its valence is 4. It can only form 4 bonds. We did that, I think, in the very first Crash Course chemistry video. But we can just take it as a rule. Carbon should have ideally 4 bonds. You cannot exceed that and go to more than 4. Again, anyone who's done more chemistry, you might want to argue with me and say, actually, it's possible. Yes, that's true, but for GAMSAT, never more than 4. We can use that principle all the time. The other thing is you can never attach an anion to an anion. So what that means is a negatively charged particle to a negatively charged particle. If you're trying to do this, they literally like charges repel, right? So if you're trying to like reassociate and move stuff around and you're going, oh, maybe I can put this with this. If it's negative and negative, or positive and positive, I should say, they're not going to glue together, right? So that's a no. You need to switch negative and positive or something else. And then here, plus or minus, so that meant like just shorthand, I'll explain it. So an increase or a decrease in the number of atoms in the system. You can't do this either. So an organic pathway should account for everything that was there before the reaction started to everything that was after. They'll be in different positions. Maybe there'll be 2 products and only 1 reactant and so on. But if you count up all your hydrogens, all your carbons, all your oxygens and so on, there should be the same number on the left side as there are on the right side. Cool. So those are just some of the basic principles that we'll carry through, and I'll kind of point these out as we go through. So now the bulk of it is just going to be understanding what are the most common types of reaction pathways so that you can recognize them and then be familiar in using them. So the first is substitution of haloalkanes. So a halogen or a haloalkane is an alkane with a halogen attached. That is your group 17 compounds or atoms. So this would be fluorine, chlorine, bromine, and iodine, right? These are the most common. You'll mostly see chlorine and fluorine being used. And so I've done that there in green. Anywhere where I write R, that is just shorthand for more carbon chain, right? Truthfully, it could be another hydrogen as well, but I'm going to assume that it's a little bit more complex. Anyway, you see R, it just means the rest of the compound keeps going in both directions. If we were to react a haloalkane with something like a sodium hydroxide, you can see the hydroxide is negatively charged on its own, right? If it were to be ripped away from the sodium, which it would dissociate in water, and halogens all form negative ions as well. So because they're both negative, they're interchangeable, we'll say, right? So what's going to happen is the hydroxide is literally just going to go and attack this bond. It'll pull the halogen off and it'll replace it. We'll see it there. And what I should have done, I broke my own rule here. I've got to account for everything else. The sodium needs to attach to something, and that is the halogen would go with it. So say that was chlorine, then that would be sodium chloride, and so on, right? A salt, like that. And so what we've now made is an alcohol, right? So understanding functional groups, again, we did that in the previous one, the first of the organic chemistry, which was the third crash course video, if you want to check that out again. But this here is our haloalkane. We can react that with a base, and it turns into an alcohol. Just like that, we can summarize it. We go, okay, cool. So now any other haloalkane that's put in the presence of a base will form an alcohol. And we should be able to just play that puzzle, right? So then next we have addition of alkenes. So addition of alkenes, this is where you've got an alkene, so a double bond, and you're adding something across the double bond, right? So you're saturating that double bond. And so here we've got HX, so again, X is just a halogen. So this could be like hydrochloric acid, or it could be HBr, so hydrogen bromide or bromic acid, and that kind of thing. If we add that, we've got a H plus, and we've got, I'll do X. We've got an X negative. And then each of these are going to attack one side. So one will attack here, the other one will attack to the other carbon, and you'll see them attach. I've actually done them backwards to the way I did the product. So let's say that this one attacks this carbon and this one attacks this carbon. But these carbons already have their 4 bonds. We can't go more than that. So what it'll do is it'll actually be breaking one of these double bonds, removing that, and then now there's a spot available on each carbon, and that is where they'll take their place, like this. And so now we've ended up with a haloalkane. So an alkane with a halogen attached. And there we go, right? So that is an example of an addition of alkenes. Now, one thing is we do have to watch out for something called Markovnikov's rule. So Markovnikov's rule, apart from it being an absolute tongue twister of a name, is it says that when you're adding something across a double bond in addition, the hydrogen out of the two, so you've got hydrogen and the X, the hydrogen will attach to the side that has less hydrogen. So it's almost like it's trying to balance that out. So if I draw out another simple example and prove this, if we have butane like this, and then we've got butene instead, this would only be able to contain 2 carbons. On this side, you could have 1 here. This carbon would have 2 more spots for hydrogen. And then this spot here would have 3 more spots. And so if we look on either side of the double bond, if I were to be adding H and Br, right, bromine, then if I look to the left, I've got 1, 2, 3, 4, 5, 6 hydrogens. On the right side of the bond, I've only got 2. So Markovnikov's rule would say that the preference would be to add the hydrogen to the right side, to this carbon here, because it's got less hydrogen, to try and bring it up and try to close the balance a little bit more. And on this side is where the bromine would go then, like that, and then this would become a single bond, right? And this would then make 2 bromobutane. But it is still possible for it to go the other way. It would just be less common. So this, what I've drawn here, following Markovnikov's rule, would be referred to as the major product, meaning that it is the majority of the product that is formed, but a minority of the product will form the other way around. So that will be where instead the bromine attaches to this side and the hydrogen goes on the side that has more hydrogen, and then that would be a slightly different isomer. That would be bromobutane, or 1 bromobutane. This was 2 bromobutane, this is 1. So that's how we apply Markovnikov's rule, and this would be the minor product. Like that. Cool. And then the other kind of application of addition of alkenes is saturation of fatty acids. They do this one a lot. So fatty acids in triglycerides, and in like membrane structure and that kind of thing. Draw them out. So we've got carboxylic end like this, and they just have a bunch of carbons, right? And they're usually 30-something carbons long, but some of them have double bonds in them. So if you've got a double bond, say here, you can actually add like hydrogen gas, for example. And the idea is here, Markovnikov's rule doesn't really matter because we're adding hydrogen to both sides, so it's going to be equivalent. And then what that's doing is it's breaking the double bond off, making it into a single bond, so I might just do this, and then it's adding the hydrogen to each side, like that, and saturating the double bond. And so what that means then is you can create a mathematical ratio. If N is equal to the number of carbon-carbon double bonds in the fatty acid, well then that would mean you would need like N times the hydrogen, because for each double bond you need a hydrogen molecule. So if you had a rule, you could have fatty acid, we'll call it an N fatty acid, meaning N is the number of double bonds, plus you would need N lots of hydrogen, right, to then make the saturated version, to fully saturate it, meaning that all the bonds become single bonds, like that. And that's another example of addition. Cool. All right, so then jumping on next. So the next one now, this one's a really important one. So oxidation of alcohols. So we'll do a whole video just on redox chemistry that'll go into organic and inorganic redox. But here we're just going to look at just the oxidation of alcohols in organic pathways. What we can think of oxidation as is it's the loss of hydrogen and it's the gain of oxygen. Both of those are equivalent to oxidation. So therefore reduction, which is the reverse if you're not familiar, don't worry too much, would be an increase in hydrogen or a loss of oxygen. We're not going to look at reduction though. We're just going to look at oxidation. So first of all, we've got primary, secondary, and tertiary alcohols. So just a quick review on this. Remember that primary alcohols are compounds that have an alcohol group. And if we call this here carbon alpha, so the carbon that the alcohol group is attached to, the primary relates to the number of carbons that are attached to that particular carbon. So that would mean that we would have 1 carbon attached. And that means that all of the other positions on that carbon alpha have to be just hydrogens. So really what this means is a primary alcohol is an alcohol where the alcohol group is on the end carbon. It's on the end of the chain, right? And so if we go and try to react that, and we can use our reagent, so you wouldn't be expected to know reagents, by the way, but we'd use acid and permanganate. As an example, you could use dichromate. This here is going to be our oxidizing agent that will cause the oxidation. And it happens in 2 stages. So the first thing that happens is this hydrogen here is going to get removed, and one of these will have to get removed in the process, right? So that'll make a hydrogen gas, and that is, you can see, a loss of hydrogen. So what that'll lead to is, I probably won't bother with the color coding now, carbon alpha. So this would become just O. This would go to carbon. You've still got this hydrogen here, but this carbon's got 3 bonds and it needs 4. And this oxygen also only has 1, it needs 2. So you make a double bond here. And so what you end up with is an aldehyde. But then it can keep going, so then it will keep reacting, because obviously remember it's in the same bucket with that same acid and permanganate. It can actually continue reacting and do a second layer. And what's going to happen in this case is now it's not going to be reducing or losing hydrogen, it's now going to be gaining oxygen. So we're going to see an oxygen being added to this hydrogen here. So what we'll see now is carbon, carbon alpha, double bonded oxygen. Now we're going to see OH instead. And all of a sudden we have a carboxyl group, right? Or a carboxylic acid, like this. And so we can think of that generally meaning that primary alcohols oxidize through an aldehyde group and then into a carboxylic acid. And so then the next one's secondary alcohols. So same thing, if we draw in carbon alpha, there's our OH group. Now we're going to have 2 carbons attached, right? Meaning that really this hydroxyl group is on the middle of the carbon chain, right? Even though it's kind of on a bend, just means the carbon chain is running this way. Secondary alcohols have an alcohol group not on the end carbon, but in the middle carbon. And then what's going to happen there is it's going to try to do the exact same thing. So this is the great thing, as long as you know the first one, you technically can predict all of the others. And I don't think they would even get you to predict it necessarily. So it's going to try and remove a couple hydrogens, which it can do. And that will then lead to like this, and this will go to a double bond. And what we have now is a ketone. Right, we don't have that hydrogen to make an aldehyde. And if it tries to do it again, it's going to try and add an oxygen. But if you remember last time we tried to add oxygen to the hydrogen, this time there is no hydrogen attached. So what that means is there is no more reaction, it just forms a ketone. And then if we go again on tertiary, that just means that it has 3 carbons attached. So carbon alpha, hydroxyl group, carbon, 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 like this. And it can't even do the first step, because as soon as you try to add acid and permanganate, the first step was remove hydrogen. And although it'll try to remove this one, it needed another hydrogen either here or here to help balance it, and it's not going to be able to do it. So what that means is you get no reaction at all. You cannot oxidize a tertiary alcohol. There we go, and that's how we can predict the 3. And notice that all of this, you could just do it off of pattern recognition. They'll give you an example, and you just go, oh, okay, so I can see the difference is it's lost a hydrogen from here and here. You could extrapolate that to any other compound, and it'll still work. Then you've got condensation, polymerization. So again, a bit of a tongue twister of a name. Condensation meaning a reaction that forms water as a byproduct, the condensation of water. Polymerization forming a polymer, making a chain out of smaller things. So esterification is one type. This is where you form esters. So an ester is effectively formed from an alcohol plus a carboxylic acid. So leaving out a lot of the detail, if I just draw in an alcohol group like this, and I'm just going to put R like that, and then I'm going to put next to it a carboxylic group with R like that. Let's call this R1 and this R2. You can see that facing each other right here, we could form a water molecule. You can see H2, there's 2 hydrogens, O. So this is where our water is going to come out. And then what that means is everything is going to be glued. Where that pink box is, everything is going to be glued together. So that would mean we have R1, carbon, and then we have oxygen. Then we hit the pink box, so we just draw a line right through it. And then what does it jump onto next? If we ignore the water, straight to a carbon. And then that we just keep copying like that. There's our ester, right? And so the ester linkage is this thing here. You can think of it as cook. There's our ester link. And we can't forget as well, water was made as a byproduct. That way now we've accounted for all the stuff on the left, on the right. So that's esterification. And then amides. So amides are where we have an amine group, which is an NH2, and then a carboxylic. acid. And it works almost exactly the same way. So you're just not connecting through an oxygen, you're connecting through a nitrogen now. So if you have a carbon and then you've got NH2 like this, same thing, so back to a carboxylic, like that. I'll call this R2 again, and this here we'll call R1. Same thing, we can find water in the middle, just here. And you can see again, like I said at the start, you can't substitute a hydrogen if it's attached to a carbon. And that's exactly what we're doing. That's exactly what we're not doing here. These hydrogens are attached to nitrogens and oxygens. So that's why they can get interacted with. And the same thing, right? So now you'll have a link. So you'll have R1 copying it left to right, carbon, nitrogen there. Then we hit the box. So we cut the box out, we go straight to carbon, double bonded oxygen. I'm going to flip the double bonded oxygen this way. They'll try to maximize their distance between each other. You wouldn't need to know that for GAMSAT though. And there's our amide link, right? So it's like a little, almost like a Tetris piece, like that, or a Z. And yeah, this is our amide link, or peptide bond. If you're looking at it in terms of amino acids, that's some way that they could apply to bring in a little bit of bio, linking amino acids into a polypeptide. And then again, water is a byproduct, making it a condensation reaction. And then finally, just a little bit of alkylation, or Friedel-Crafts alkylation. They don't do these all that often. And again, these are much, much more visual. The basics of it is you're adding an alkyl group, so a carbon chain of some sort, to an existing carbon compound. So they usually do benzene rings, and then you use aluminium trichloride as your catalyst, along with an alkyl group, which we'll call R, to a halogen, like a chlorine. And the catalyst is going to help this happen. All that you're really going to do is you're going to cut off the chlorine, and then that'll help you glue the R directly to the benzene ring, just like that. And it'll be replacing a hydrogen. So we said you can't replace hydrogens, right? You can if there's a halogen involved. So before we had the halogen on the carbon chain, right? This time it's actually kind of like this. This is like our carbon chain over here with a chlorine, so it's a haloalkane. And then we're substituting the chlorine for a hydrogen, and then that way then we glue this onto the benzene ring. And it could have been to any of these, but they'd all be equivalent. And then that forms an alkyl benzene, like that. Cool. All right, so that's everything for the reaction pathways. You can see, like, yes, I've just gone through bang, 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 bang. That's more so you're familiar, but really it's a visual thing, right? Like, think of it as Lego bricks. Look at what's moving, look at what's no longer part of the compound, where did it go? And then extrapolate that to any other compound. You'll be fine. So then next up, we've got just some acid-base equilibria. So some of these formulas you will have seen in the maths video. Let's just quickly go through them. So first of all, acids and bases on the left here. Acids are proton donators, bases proton acceptors. Then we've got the dissociation reactions in the middle here. So when you put acids and bases with water, they dissociate or split, and acids form hydronium, which is equivalent to H+. You'll see me write H+ and H3O+. They're interchangeable, treat them as the same. That is your form of acid. And then A negative, which is the conjugate base of the original acid. There we go. So this here, this is acid. We have water. This would be the conjugate acid of the water. You can see they're kind of connected. And then the A negative would be the conjugate base of the acid. It's kind of like the carcass or the leftovers of the acid. And Ka is an equilibrium constant expression, written like this, same as we did in the equilibrium video. You just leave out water, because that actually is acting as the solvent at the same time. And Kb's as well use the dissociation of bases. So you've got base plus water makes conjugate acid of the base plus the conjugate base of the acid, which is water. Water can act as an acid or a base. It doesn't really care. Put it with an acid, it'll go cool, I'll be the base. Put it with a base, it'll go cool, I'll be the acid then. It's interchangeable. And then some P values. So P just means negative standard log of that value, mathematically. So the pKa is the negative log of Ka. The pKb is the negative log of Kb. The pH is the negative log of the H concentration. pOH is the negative log of the OH concentration. And we can also say that pH plus pOH should add up to 14, because that is the pH scale. That comes from the solubility product of water just 10 to the negative 14. There's the pH scale right there. So a simple way to think of measuring basicity and acidity is if you take the pH scale, whatever the pH is, the leftovers of 14 is the pOH. It's a really quick way to convert it. Effectively, we're just rearranging this formula that we wrote down. So therefore, pOH should just be 14 take away pH, like that. So it's almost like it takes up a margin of the actual scale to 14. So if it's pH 5, its pOH would be 9. Low means strong, high means weak, but it depends on what you're talking about. So if you're talking about acidity, low pH, because that's a measure of acidity, means strong acid. High pH means weak acid, or really very strong base. So weak of an acid that it's actually a base, and vice versa. So if we took an example compound that has a pH of 5, it would have a pOH of 9. So pH of 5, that is a weak acid. pOH of 9 is a relatively weak base. Because remember, a pOH of 9 is actually quite high. High pOH means weak base, because it's measuring basicity. Like that. And so it makes sense. Weak acid, weak base. It's kind of in that middle frame, right? If we were to take something like something with a pH of 1, that would be a very strong acid, and that would have a pOH of 13, and that would be a very, very, very weak base. And so a different way to think of the scale is just like this. You just think strong acid, strong base. The pH scale can run 0 to 14 left to right. pOH then must run in reverse. It's up to you how you want to think of it. Cool. All right, so getting more into buffers, right? This is the one that's a little bit more complicated, and again, something that seems to be getting phased out of GAMSAT. It's in the practice material, but again, haven't seen it, didn't see it in March. I think this one came up again in test 1, the green book from ASA. That one seems to be the most kind of content-based and is definitely not as reflective as tests 2 and 3. So they're definitely moving towards reasoning, and that's probably just because they're trying to split the crowd. I mean, if it's really too content-based, people can just over-prepare. They can use videos like this, and then all of a sudden they've got the answer. What needs to happen is there needs to be a way to split the crowd, test people's reasoning with it, so it's not just a test of memory. So with buffers, the whole goal of a buffer is to create a solution that will resist pH change, right? So if you've already got a mixture of acid or base, then you want to try to keep that pH the same. So that could be because there's like oxidation that may occur, maybe because it's going to come into contact with other compounds or whatever. So we can have it either as a mixture of acids or a mixture of bases, depending on whether or not we're trying to keep something acidic or something basic. If we're trying to keep something acidic, we'll have a mixture of weak acid and its conjugate base. If we're trying to keep something basic, we'll use a weak base and its conjugate acid. And so what's really happening here is if you've got, for example, why do we use a weak acid? So if we look at this here, this is going to be representing the left-hand side of the dissociation, and this is going to look at the right-hand side of the dissociation. So therefore, if equilibrium sits closer to the left side, it means it's favoring the production of HA or acid, therefore at equilibrium there's going to be a lot of it. Versus if equilibrium was sitting closer to the right side, then it would be higher amounts of its conjugate base at equilibrium. Weak acids have K values that are much, much less than 1. A K value of 1 would mean that it's equally balanced between the two at equilibrium. Much, much less than 1 means it's pushing further to the left, and that's why I've done it as a scale like this. So if equilibrium is sitting for a weak acid further to the left-hand side, it's favoring a yield of acid at equilibrium. And that's a good thing, because what that means is that if you've got more stuff over here at equilibrium in that buffer, when you add a base to it, you've got a lot of acid ready to neutralize that base and delete its effects overall. So here I've put an example explanation of it. If you've got base plus acid, what that's going to do is it's going to lower the left-hand side, right? Because you would literally be consuming up your acid as it gets eaten up by the base in the neutralization process. Equilibrium, or Le Chatelier's principle, would say, well, if you lower the left-hand side, then it's going to favor the back reaction all of a sudden. It's going to try to re-achieve equilibrium. And if that's still somewhat new, check out the equilibrium video. I think it was the first crash course video, but don't quote me on that. I'll link it at the bottom if you haven't already seen it. I go into a lot more detail about Le Chatelier's principle. Worth watching. So if we add base, it'll consume our acid, it'll favour the back reaction. That will then lower, it'll consume our H3O plus as it tries to re-establish the equilibrium, and that's going to then raise the pH, which makes sense. If you add base, pH goes up. We want to avoid that. So if we were to add a buffer with it, what that means is with the buffer added, we have heaps and heaps of HA because its equilibrium sits on that side. And so what that means is that now when you put the base with it, you still have a consumption of acid, but because you have such a gigantic stockpile of acid, it's going to be a relatively insignificant drop. So you will get a re-establishment of equilibrium, and you will get a loss of H3O plus, and therefore an increase in pH. But because it's relatively smaller, because you've got a big stockpile of acid from your buffer, then it means that the pH is not going to have to shift as much overall. You'll be able to retain a fair chunk of acid and retain that pH level. And then vice versa, if you were to do a buffer with a base, it's everything but in reverse, right? You have a weak base, you add an acid to it. If you've got enough of a weak base buffer, then that will retain the higher pH and prevent the base from being consumed, equilibrium being re-established and pH dropping. So that way then your buffer is working to maintain a relatively stable pH. It's never going to be perfect, but it'll massively reduce the loss or the gain in pH. And so if we just look at a bit of the stoichiometry of it then, actually before we do that. And so I missed over here, we can also then summarize everything in the Henderson-Hasselbalch, I think is how you pronounce it, equation. pH is pKa plus log 10 of base over acid. They usually give this one in the questions as well. What we want to do is just, again, have more of a qualitative understanding of it. So what if this ratio of conjugate base to acid was between 0 and 1? What would that actually mean? Well, if we put that into the formula, pKa plus then log 10, and then something that is between 0 and 1. I would look at the limits and go, well, log 10 of 0 is undefined, so it's not possible. You can't actually have 0. Log 10 of 1 is going to be 0. And so what that means is that this would be pKa. So if this is a fraction then of 1, what that would mean is that the log 10 would actually be a negative number. So you'd end up doing take away some value. So that might be, let's just call it x. And so what that means is that pH should be less than pKa, because pH is whatever pKa is, take away some number, like that. So then what about if it was greater than 1? So if it's greater than 1, now we would be doing pKa plus log 10 of something greater than 1. That kind of depends on the relative size of it. So log 10 of 1 is 0, right? So that would mean that anything greater than that is going to be greater than 0, right? It's going to be positive. So therefore we're adding some positive number. So therefore we can say that pH is greater than pKa, like that. And then it says which condition would give a pH of 16. So that one's just a straight maths question. So 16 is equal to pKa, like that, and then plus log 10 of acid, oh sorry, of base over acid, like this. And so that would mean that 16 is equal to pKa. Now remember, pKa's, they have to be under 14, right? So if this is under 14, then it means we have to be adding 2. So what that would mean is that at least this has to be a log 10 of 100, right? Because that would be a 2, at least. It may be more, so that would mean greater than or equal to. So that would mean then, if the log 10 of A negative over HA is greater than or equal to 2, then that would mean that the ratio, this is the condition now, of these two here would have to be greater than or equal to 100. And we could solve that, we could rearrange it. That would mean that the concentration of conjugate base would have to be greater than or equal to 100 times the concentration of the acid. Like that. There we go. Cool. And so if we look, now we'll do an actual stoichiometry question. So for example, if you produce a 1 litre solution from equal parts 1 molar acetic acid and 2 molar sodium acetate, calculate the pH if the Ka value of acetic acid is 1.8 by 10 to the negative 5. So again, without a calculator, right? So it's just estimation techniques. First thing you always do is do an ice table, right? So initial, change, and equilibrium. So we draw out the reaction pathway here, and it's just a dissociation. So this is our HA, this is our H2O, this is our A negative, so our conjugate base, and this is our H3O plus. So even if you didn't really know how to do the balanced equation, you could just write it in general form and still work with it. And so initially, because we had equal parts, that means equal volume. So that means that N is equal to C times V. So for the acetic acid, that was 1 molar times half a litre. So 1 times half is half. And over here, we had sodium acetate, which is this stuff. And that is 2 times half, right? So that is 1 mole, like that. And apparently we had no water and no hydronium at all, but it's in solution, so, but we'll leave it as 0. The change then is going to be, well, it's going to try to establish equilibrium. So we're going to consume the acetic acid, so we're going to lose X amount, and over here we're going to gain X amount, and we're also going to gain X amount of hydronium. So then we can create expressions. At equilibrium, there'd be half a mole take away X, 1 mole plus X, and then X mole. So concentrations, we would divide them all by the volume, but the volume is 1 litre. So dividing them all by 1 is going to keep them the same. And this is where then the kind of assumptions come in. Since the Ka value is close to 0, it's 1.8 by 10 to the negative 5. It's really, really small. Given that's really small, we can assume that X is approximately 0 as well, right? The change is very, very little and it's insignificant relative to our calculations. The important thing is that when we do that, we don't make this one 0. So here we let X equal 0, we do 0.5 take away 0, it's basically 0.5. 1 plus basically 0, basically 1. We're going to keep this one X though, because if we put that as 0, it'll cancel everything out. And the reason why is if we come down here and we get our Ka expression, that would be the concentration of the two products multiplied together and raised to their powers, but they're all 1. And then over the Ka, so over the concentration of the reactant, right, which is 0.5. If we made X 0, this would just be 1 times 0, the whole thing would become 0, and it would stuff it up. So we're going to leave that as X, so therefore we get 1 over half, which is 2X, should be 1.8 by 10 to the negative 5, and then we can solve X, 9 by 10 to the negative 6. Just as a quick review, how have I done that? So there's a couple of ways. Probably the easiest is to scale this to 18 and down to negative 6, and then we're dividing the 2. So then I just cancel these, 9 by 10 to the negative 6. And there we go. So that is our Ka, or that is our X, right? And remember, X was the concentration of hydronium, which directly relates to pH. And so we can do that. So we can go, okay, well, if the hydronium is 9 by 10 to the negative 6, then we'll kind of estimate that to be basically 10 by 10 to the negative 6, which would be 1 by 10 to the negative 5, and therefore the pH would be the negative log. Because remember, pH is negative standard log of H+, and so that would be the negative log 10 of just 1 by 10 to the negative 5 is 10 to the negative 5, and we can use our log laws. So again, check that video out. Bring this down here, the double negative becomes a positive, 5 log 10 of 10, log 10 of 10 is 1, and we get pH of 5. There's our pH, right? So now what we're going to do is look at how the buffer actually works. So this is just when it's in equilibrium. Now we're going to go and add a base and try to throw it out of balance. So if we do that, if we add 0.02 mole of sodium hydroxide, now a very, very strong base, we're going to see what it does. We're also going to use this fact, because there's no way you'd need to know this. Log 10 of 2, we're going to estimate as 0.3. So again, we do the neutralization reaction now, right? So base plus acid makes salt plus water. We just care about what's going on over here more than anything. And I guess our conjugate, so this is our conjugate here. The sodium's there, but it can jump off and make our conjugate base. So now we're already at the equilibrium. So our initial now is actually the equilibrium numbers. So we've added 0.02. Remember we had 0.5. at equilibrium was effectively 0.5, and this was effectively 1. Now we're going to assume all of that reacts, right? So therefore, 1-to-1 ratio, the same mole of that acetic acid will react, and then we should gain 0.02 mole of our acetate, right? So then, if we do the calculation, 0.02 take away 0.02 is nothing. Then acetic acid, 0.5 take away 0.02 is 0.48, and then here we're going to gain 0.02 to 1.02. And again, we divide them all by their volumes, which is 1 litre, 1 litre. We get our concentrations, which are the same. And then we can go into the Hasselbalch equation. So pH is pKa, so that is negative log 10 of 1.8 by 10 to the negative 5, plus log 10 of, this is our A negative, this is our HA, so that's 1.02 divided by 0.48, and then we've got to evaluate. And so what I've done here is, in this case, I'm using a log law. I'm kind of splitting it and separating it a little bit. So I'm going to put the negative out the front. I'm going to think of multiplying these as the same as adding their two logs. So you can see here I've added them, a standard log of 1.8 and a standard log of 10 to the negative 5. And so then if I do that, log 10 of 1.8 is basically log 10 of 2, which the question tells us is 0.3. And really it should be a little bit less than 0.3. So maybe what I'll do is change this slightly actually and call it like 0.28 instead, right? Because 1.8 is less than 2. Log 10 of 10 to the negative 5 is just going to be negative 5, right? These cancel out, just get the power. And then plus, and then over here, I'm like roughly estimating 1.02 over 0.48 is basically 2, right? It's basically 1 over half. And log 10 of 2 is 0.3. So now I'm going to change this slightly. So 0.28, then take away 5 is going to be negative 4.72. And keep in mind as well that that there had a negative on the front of it. So then it becomes 4.72, and then plus that 0.3 from here, and then finally we get 5.02, like that. So I wrote here no change because I had a rounding error, but now you can see it's gone from pH 5 up to 5.02. So adding the base has increased the pH, but because of the buffer, it's barely changed it, right? The buffer basically gobbled it up and consumed it and left behind a lot of acid still because it's a weak acid that favors the acid position in equilibrium. And there we go. Cool. So that's a bit of a heavy topic. Like I said, the stoichiometry is probably good to run through yourself a couple of times. I'll try to make like a worksheet maybe for this on the resources page, but just to kind of practice it. But realistically, they're probably not going to get you to do heavy stoichiometry because they're multi-choice. A lot of the time they want you to rank things. So understanding how the buffers work though, that's why I go through the maths. Understand how they work can actually help you with the ability to reason more qualitatively. So hopefully that's a good run through of the second part of organic. All we've got left for organic chemistry now is the stereochemistry and stereoisomers, which I know people are probably eager to see. It should be a relatively small one though, weirdly. There's not really a lot of content to it, it's just very, very commonly asked. So it's overrepresented, I think, in GAMSAT, but it's not actually a gigantic topic. They don't go right into all forms of stereochemistry. And so we'll knock that out. Hopefully I can keep that one under half an hour, trying to keep them as kind of bite-sized as possible where I can. But otherwise, if you haven't already, subscribed to the channel if you're kind of watching through, because then you get notifications, you see everything. I've also linked now as well. I've created like an Instagram. I haven't really posted on it because I'm not really an Instagram person. But I figured that I'll do that as a way to keep people updated with what is happening each week. I don't know how frequently I'll post because that's not really something that's on my mind. But if you're interested in that or any kind of behind the scenes stuff, any kind of communication, it's a little bit easier to chat to people and stuff as well. Then I will have that up. So I'll link that at the bottom, check that out as well. And then otherwise, I will see you guys in the next one.